All right. So we will continue further with the oscillator circuits. Okay. So just a very quick recap, okay, of what we have studied with respect to oscillators. We looked at the concept of oscillators with respect to uh, the positive feedback, Barkhausen's criteria. Okay, so there are two stability criteria. The first one is related to the phase shift, which says it should be an integral multiple of 360 degrees, and the second one is regarding the loop gain. Okay, for sustained oscillations, the loop gain must be equal to 1. Okay, so that was the block diagram of a oscillator circuit. So these are how the steady state oscillations eventually build up. So there are three types of oscillations: sustained, exponentially increasing, and then the damped oscillations. In the previous session we discussed about RC phase shift oscillator, okay, wherein the feedback stage is purely based upon R and C components, right? The frequency of oscillations is given by the expression 1 upon 2 pi RC square root of 6, and the beta factor is 1 upon 29. Okay, so for sustained oscillations, the condition which has to be satisfied is that the gain of the amplifier must be at least greater than 29, so that the oscillations will begin. Okay, so that was the complete circuit of a RC phase shift oscillator. The first one is using a FET and the second one is a BJT version, and we focused on the FET version. Then the next type of RC oscillator was a Wien bridge oscillator. Okay, so here we have more number of resistors and more number of capacitors, especially the resistors, okay, and the capacitors are so nicely arranged that it forms a bridge kind of a network, wherein combination of resistors R1 and R2 and capacitors C1 and C2 form the frequency adjustment elements, and the resistors R3 and R4 form the feedback path. Okay, so that was the complete Wien bridge oscillator circuit. So instead of a normal amplifier, we are using a operational amplifier, but in any of the cases, a normal amplifier can also be used. Okay, so today we will be discussing on another type of oscillators wherein the feedback network is not of RC components, instead it is of inductor and a capacitor. So it's a combination of a inductor and a capacitor. Okay, fine. All right. So the basic configuration of a resonant circuit oscillator. So now we have come across a new word called as resonant circuit. When we studied an RC phase shift oscillator or a Wien bridge oscillator, we never came across the word resonant because there resonance doesn't happen. Okay. Now what do we mean by resonance in general? Okay, see, resonance property is usually obtained in resonant materials, wherein at a particular frequency you will be getting the highest current, okay, a peak current, whereas at other frequencies the peak current will not happen. Okay, so it is only at a particular frequency, and that particular frequency will be determined by the reactance of the inductor and the capacitances. Okay, so in simple words, we usually call the combination of L and C as a tank circuit. Okay, so this particular tank circuit is responsible for the resonance phenomena, and this resonance phenomena occurs at a particular frequency, and this particular frequency is being determined by the reactance parameters. So this particular frequency is determined by reactance of the capacitor and the inductor. Okay, so whenever we say reactance of the capacitor and the inductor, we usually denote them by the symbols XC and XL. Okay, and most of the times it so happens that when XC becomes equal to XL, we will be getting peak resonance. Okay, so usually that is the thing which happens in the case of the tank circuits. Now the same tank circuit is being used in the feedback section of this particular oscillator circuit. So if we want to denote it explicitly in this particular oscillator, then this is where the tank circuit consists of. Okay, normally if X1 and X2 are capacitors, then X3 will be an inductor. If it is the other way around, okay, suppose if X1 and X2 are inductors, then X3 will be a capacitor. Okay, now you have to understand that the sole purpose of using the inductor and the capacitor is again to obtain a phase shift of 180 degrees. Okay, so that is the sole purpose, and one special feature of this particular tank circuit is that we will be obtaining resonance also. Okay, which is usually not possible in the case of a normal RC circuit. Okay, all right, so that was about the block diagram of a resonant circuit oscillator, where again there is an amplifier which provides you a phase shift of 180 degrees, and there is a tank circuit. We also call it as a tuning network, the tuning feedback network, which consists of a combination of L and C. Okay, now again in tuned oscillator circuits we have subtypes. The first one is Colpitt's oscillator, wherein the reactive elements, okay, X1, X2, X3 are the reactive elements or the reactance elements. So in a Colpitt's oscillator we have two capacitors and one inductor. In a Hartley oscillator we have two inductors and one capacitor. If it is tuned input and tuned output, okay, a combination, then we will be using LC as X1 and LC as X2 also. Okay, but this is more of a mixed kind of an oscillator. We will be focusing on Colpitt's and Hartley oscillator, okay, in the coming slides. So let us first look at a Hartley oscillator. A Hartley oscillator can be constructed using a BJT, it can be constructed using a JFET, it can also be constructed using even a MOSFET also. Okay, in this particular slide, and for your syllabus, since we are focusing, okay, we are specially focusing on JFETs. Okay, so most of the circuits will be using JFET as the core device. Okay, so here also we have a JFET which is being used as an amplifier. Now if you just look at the biasing, it is more of a self bias kind of a circuit, especially with respect to the amplifier. Okay, so just denote it. This particular section is your amplifier. Right, okay, so that's your amplifier. Instead of a normal resistor, in your biasing circuits, we normally use the resistors, right? Okay, so we can use resistors here also, but it is more preferred to use a radio frequency choke, okay, instead of a resistor. Okay, it's an inductor itself. The purpose of using an inductor here is that RFC blocks any AC component if present, any AC component. Okay, so you can clearly observe that at the drain side, by the way, this is drain, gate, and the source of this particular JFET. So at the drain side we are applying drain voltage plus VDD, and it's a pure DC signal. But in case if there is any AC component present, okay, then that will be completely blocked by this particular radio frequency choke. Okay, so it blocks any AC component and allows only DC to flow. Okay, so that's the sole purpose of using a RFC. This also helps to some extent with respect to the voltage gain and the stability of the overall amplifier. Okay, fine. So that is one thing. And CG and CC, both of them act as coupling capacitors. Okay, their sole purpose is to block the DC and allow only AC to flow. Okay, so this is very interesting, right? See, the sole purpose of the coupling capacitor CC is to couple the output signal which appears at the drain of the amplifier to the feedback network. Now where do we have the feedback network? Well, I'll just represent it by some different color. Okay, so our feedback network is being represented here. Okay, so that's the feedback stage, which consists of L and C tuned circuit. Okay, so the coupling capacitor CC ensures that the output is coupled to the feedback network. Okay, fine. Now let us just focus on the feedback network. Okay, we know that the amplifier has done its job. Okay, it has just amplified whatever input signal has appeared at the gate side, and we have an output signal V0. So this particular output signal now has to be coupled to the feedback network. So when it is coupled, well, we are using L1 and L2, and please understand this is a center tap here. Okay, we could have used a single inductor whose equivalent inductance would have been the summation of the two individual inductances which are being used here, L1 and L2. Okay, for example, see, L equivalent is equal to L1 plus L2. Okay, instead of L1 and L2 we could have used only L equivalent. Okay, now why are we using a center tap and then L1 and L2? It is just to ensure that the feedback network's signal which is being produced has a phase shift of another 180 degrees. So this ensures that there is 180 degree phase shift, because altogether we know that an oscillator to produce oscillations must ensure that the Barkhausen's criteria is satisfied, and the first criteria is that the phase shift must be an integral multiple of 360 degrees. Okay, fine. Now what actually happens in a LC network? Well, you must have gone through the concepts of network analysis, where what actually happens within a L and C. Okay, fine. So now let us very quickly try to understand. See, L and C is a combination of, I'll just be drawing an inductor here and a capacitor. Okay, it could be in series or it could be in parallel. Okay, not a problem. So we have this thing, right? Now let us just assume that initially the capacitor is being energized, okay, by applying a voltage. So here we can just assume it to be V0. Okay, V naught is the output voltage. So due to this output voltage, a current is flowing, and whenever we say current, okay, charges, right? So due to the charges that get built up on the plates of the capacitor, an electric field gets established. Okay, so once this electric field gets established, it forces, okay, the charges to get discharged from the capacitor, right? See, the sole purpose of a capacitor is to ensure that there is charging as well as discharging. So once the capacitor gets charged, after some time, obviously it has to discharge. So when we say discharge, the charges are being moved, right? Okay, I'm sorry, they should be negative. Okay, so the negative charges will be flowing. And what do we call the movement of charges or the flow of charges? It is nothing but current. Okay, so a current flows through an inductor now, right? So, and we know that whenever current flows through any inductor, magnetic field gets established. Okay, and we call the magnetic field by symbol H, right? So now you can just correlate your some of your field theory concepts. An electric field denoted by the vector and magnetic field denoted by vector H. Okay, so now in turn, magnetic field ensures, or it again produces a current. Okay, and the current, in the sense, again charges will be flowing and then they get established on the capacitor. So this is an ongoing process. Changing electric field produces the current, and changing current produces a magnetic field. Okay, now again, so it's like magnetic field through an inductor and electric field through a capacitor are analogous. Okay, so this process keeps on happening, due to which you will be getting oscillations. Okay, please ensure. So this actually ensures that there are oscillations being produced. But the point is, initially they appear to be damped. So these are damped oscillations. Okay, now how do we ensure that the damped oscillations are improvised from being damped to sustained oscillations? Sustained in the sense constant amplitude oscillations. Okay, see, if the signals get damped, they eventually become zero, and there is absolutely no use of this particular oscillator. Okay, the signals should be produced continuously. This will be ensured by providing this center tap. Center tap. So this center tap ensures that the phase shift is exactly 180 degrees. Okay, so if that happens, then 180 degree phase shift from the feedback network, 180 degree phase shift from the amplifier network, altogether it becomes 360 degrees, so that you will be getting sustained oscillations using a Hartley oscillator. Okay, so now let me just remind you that the same phenomena happens in the feedback network. Okay, wherein the current flows through an inductor, and this produces the magnetic field. The produced magnetic field in turn forces the charges to appear on the capacitor. Once the charges appear on the capacitor, electric field gets established. Once the electric field gets established, again the charges will be discharged from the out of the capacitor, and it ensures that again there is a current flow through the inductor. So this is an ongoing process. Okay, fine. And finally, again the feedback, which is VF, okay, the produced output voltage will be fed back to the input of the particular amplifier. Okay, so what about the frequency of oscillations? The frequency of oscillations can be given as 1 upon 2 pi square root of LC. Now what is L? L is the equivalent inductance given by this particular expression, L1, L2 and 2M. So this 2M, M stands for mutual inductance. M is mutual inductance. So whenever there are two inductors, you know that there is a mutual inductance happening. Mutual inductance, but usually this quantity is very small when compared to L1 and L2. Okay, so while solving problems, if at all mutual inductance parameter has been given, then you can include that. If it is not mentioned, then you can just ignore and consider L equivalent to be the summation of L1 plus L2. As simple as that. Okay, fine. So I hope the basic concept of a Hartley oscillator is clear to you. Now coming to the Colpitt's oscillator, there is not much difference when you compare a Hartley oscillator and the Colpitt's oscillator. The only key difference is that in the feedback network. Okay, you just look at the amplifier stage, it is the same. There is absolutely no difference between the amplifier present in a Hartley and in a Colpitt's oscillator. The only difference lies in the feedback network. So here we are using two capacitors and the center tap is between the capacitors. Okay, just to get the proper phase shift. Here also the process is the same. Okay, it is the ongoing process between the electric field and the magnetic field between capacitors and the inductors. Okay, the only difference is C equivalent is C1 C2 divided by C1 plus C2. Why? Because we know that the capacitors are in series. The series capacitors will be given as C1 C2 upon C1 plus C2, which is the C equivalent. Okay, and the frequency of oscillation is again 1 upon 2 pi square root of L C equivalent. Okay, fine. So that was all about Hartley oscillator and Colpitt's oscillator. Then moving further, let us discuss about a crystal oscillator. Before we discuss about a crystal oscillator, let us just try to understand one or two drawbacks of Hartley and Colpitt's oscillator. What may be the drawbacks of these oscillators? See, the first point is, in the feedback network we are using a combination of L, C, and we call it as a tank circuit. Now most oftenly the resonance which happens due to the tank circuit is not so sharp. Okay, the resonance is not very sharp. What do we mean by that, not very sharp? Okay, let me just draw the resonance with respect to frequency. Okay, so we are varying the frequency. It could be current. Okay, the current which flows. Usually we get such type of resonance peak, okay, which is some sort of inverted bell shape. Okay, but this is not so sharp. Ideally we prefer a very sharp resonance of such kind. Okay, so what's the difference here? Here the resonance happens at a particular frequency. Okay, say for example if FR, okay, FR stands for resonant frequency. Now ideally we prefer such kind of a resonance, but practically using LC circuits it is not possible. Okay, because they are all passive elements and there will be some loss happening, okay, between the reactances of the inductance and the capacitances. So in order to avoid that particular problem, we are preferring crystal oscillator. Okay, now just to talk about a crystal oscillator. What's a crystal oscillator? A crystal oscillator is basically a tuned circuit oscillator itself. Okay, which means again it's a combination of L and C, but here L and C are improvised. more accurate. So it's again a tuned circuit oscillator using a piezoelectric crystal as a resonant tank circuit. So this is an extremely important point. A crystal oscillator uses naturally available piezoelectric crystals. Now, which are the crystals that are naturally available? A crystal called quartz. All of us must have heard about this term, quartz crystals. Your extremely accurate digital watches, all the smart watches, they use quartz crystal inside them. Okay, because their frequency is sharp. Okay, it gives a great sharp resonant frequency. So so the quartz crystal has a greater stability in holding constant at whatever frequency the crystal is originally cut to operate. This is something which is interesting. I hope you can see this particular diagram. Okay, it is that of a quartz crystal. Okay, which has been, these are available naturally from the earth's crust. They are being taken out, and using some extremely sophisticated fabrication processes, they are fabricated. And usually a quartz crystal is somewhat transparent in nature. Okay, and it's a piezoelectric crystal. What do we mean by a piezoelectric crystal? Let me just take an example. They are naturally available materials which possess some special property, and that special property is, let me assume that this is a piezoelectric crystal. In short, PZ stands for piezoelectric. These crystals are so strange that if I apply a mechanical stress or strain, okay, in the sense it is nothing but mechanical force itself. So whenever any mechanical force is induced on a piezoelectric crystal, this crystal gives out current or electricity. Okay, and this current varies in such a way that if I just change the shape of this particular piezoelectric from rectangular to triangular, then the nature of the stresses falling on this particular crystal will be different, so that the current being produced by the piezoelectric material will be again different. Okay, so that's a completely strange behavior. Similarly, if I pass on current to this particular piezoelectric material, then this particular structure undergoes some mechanical deformation. Okay, it's very strange, but it happens. Okay, that means there is a conversion of mechanical forces to electrical forces. And this electrical forces, and this can be controlled, okay, by just changing the shape of this particular crystal. So all right, now where are these crystal oscillators used? They are generally used in the communication transmitters and the receivers. Okay, wherever there is the concept of clock frequency, there we use crystal oscillators. What are the characteristics of a quartz crystal? The quartz crystal exhibits piezoelectric property, which we discussed just now. Then I just told you that the crystal oscillator is basically a tuned circuit oscillator itself. So whenever we say tuned, a combination of inductance and capacitance are required. Now this is a crystal material. How do I relate inductance and capacitance? Well, there is a way of doing that also. How? The inductor L and the capacitor C represent electrical equivalents of crystal mass and compliance. See, these are the mechanical properties associated with respect to a piezoelectric crystal. Okay, so whenever we say crystal mass, it is the mass of that particular crystal, quartz crystal. Okay, and the compliance also. Whereas the resistance R is an electrical equivalent of the crystal structure's internal friction. Now, I just told you that whenever any mechanical force is induced, internally the dipoles, okay, the bonds will undergo some stresses. Okay, there will be breaking of the bonds, and there will be a friction, internal friction associated. So that internal friction can be electrically associated. Its electrical equivalent is nothing but resistance itself. Right? So now all together, converting the electrical equivalents, how do we get the equivalent circuit? So that's the electrical equivalent of a quartz crystal. That's the symbol of a quartz crystal. Okay, so that's the symbol, and that is, and this is the electrical equivalent. Electrical equivalent. So in the electrical equivalent, what do we have? We have a resistor, an inductor, and a capacitor, and all three of them are in series, and their mechanical equivalents are mentioned. R is nothing but the friction, L is nothing but the crystal mass, and C is nothing but the compliance term. Now there is something called as Cm, which is in parallel with respect to R, L and C, and this parallel capacitance Cm represents the capacitance due to mechanical mounting of the particular crystal. See, any crystal, it cannot be just isolated, it has to be mounted on some particular thing, on some a base. So that particular base is being denoted by symbol Cm. Okay, so this is due to mounting of the particular thing, and the core quartz crystal is this one. Okay, fine. Now here also the process of resonance is the same. Okay, but one special thing about a quartz crystal is that, okay, let me just explain it here only. There is something called as inductive reactance, XL. Inductive reactance is associated with respect to the inductor, and it is given as 2 pi FL. Okay, so that means as XL increases, as L increases, the associated inductive reactance also increases. Now similarly, with respect to the capacitance, XC can be given as 1 upon 2 pi FC. Okay, so that indicates when C increases, XL decreases. Okay, so because they are inversely proportional to each other. Now with respect to the graph, okay, let me draw the graphs. How do they look like in short? Okay, maybe you can just relate your concepts of network analysis. If I just draw the graph of the inductive reactance with respect to frequency, then the graph is like this. As the frequency increases, so does the inductive reactance. Similarly, if I want to draw the capacitive reactance XC with respect to frequency, then it decreases exponentially. Right? Now what happens within a quartz crystal at resonance condition? Usually at resonance, okay, just write here, at resonance, the inductive reactance will be equal to the capacitive reactance XC. Okay, so that means I'll have to join both these things. Okay, so how does that happen? If I want to just overlap XL on XC, then it becomes like this. Okay, so this is the stage when XL will be equal to XC, and with respect to the phases, both of them cancel. XL and XC cancel. Now what remains within R, L and C is that the XL gets cancelled with XC whenever there is resonance, so that it is only the opposition offered by the resistor R that remains during the resistance. I repeat, at resonance XL becomes equal to XC. With respect to their phases, both of them cancel, and it is only the effect of the resistor that remains. Due to that, whenever I plot the current versus the frequency, especially during the resonance, it is at a resonant frequency that I will be getting maximum peak. So this is when XL equal to XC. Okay, it is purely due to the opposition offered by the resistance. Now I think the concept is very clear. It is due to this feature that a quartz crystal can give extremely high quality factor. See, quality factor is directly associated with respect to amplitude of the resonance. Okay, the quality factor. So you can clearly see that the crystal can provide a high quality factor of around 20,000. Okay, which is really nice. Higher the quality factor, it represents better we can say that better is the device with respect to stability. Okay, so the crystal impedance versus frequency observed in the case of a quartz crystal is like this. Well, a crystal can have two resonant frequencies. The first one is called as series resonance, when the reactances of the series RLC leg are equal to the series resonant impedance. Okay, so when they are equal and opposite, the series resonant impedance is very low. So this is that first series resonance. Okay, we were actually talking about the graph, right? Okay, so this is with respect to the current. So you will be getting a sharp peak like this. Okay, so instead of current, if I replace it by impedance, okay, then I'll have to get the opposite one, right? Okay, so it should be like this. Okay, so this is what we have obtained here. Now the special feature of a crystal is that you also have one more frequency called as anti-resonant frequency, and this anti-resonant or the parallel feature happens when the resonant condition occurs at a higher frequency, when the reactance of the series resonant leg equals the reactance of the capacitor Cm. This is one very important thing. In the previous slide, whatever explanation we did was only with respect to this series RLC. Okay, please understand. Never did we consider the effect of this parallel Cm, okay, mounting capacitance. Now when this mounting capacitance gets introduced, then we will be getting another resonance. That's the resonance. It is called as anti-resonance. Okay, so this happens whenever the series resonant leg equals the reactance of the capacitor Cm. So at this particular frequency, the crystal offers a very high impedance because both of them will be in parallel. Now with respect to application, either we can use this particular series resonant feature or anti-resonant feature, either of them, for practical application. In most of the cases, we prefer series resonance. Okay, so well, I hope that will suffice with respect to crystal oscillators. Okay, all right. So any doubts here with respect to crystal oscillators or with respect to Hartley or Colpitt's oscillator? Students, you can ask me the doubts.